this video, we're going to explore how to compute the singular value decomposition of a matrix. Now, before we even begin here, it's important for us to understand what that is. So I'm just going to very briefly write A equals U sigma V transpose. That's the singular value decomposition. That's the most important part to remember. And now let's understand what each of these is. So obviously, to calculate the singular value decomposition, you need to calculate the singular values of A. And remember that the singular values of A are the square roots of the eigenvectors, the eigenvalues of A transpose A. And that will give us the singular values. Now the first element that I'm going to explain in here is sigma. Sigma is the singular values of our matrix here. However, it's not that simple, right? Because A may not have the dimensions we want it to have. So sigma, if A is square, sigma just looks like this. It's just a square matrix with the singular values on the diagonal in descending order. But A may not be the dimensions we want, so A may end up looking like, sigma may end up looking like this same matrix here, but with a zero matrix, right? With the appropriate dimensions, so that would be n minus m, or sigma may look like this. Again, a zero matrix there. And you know, that's obviously something you'll have to figure out, but it's pretty simple to find this sigma matrix. Once you know how to find the singular values, you just have to format this so that it's of the appropriate dimensions. The more complicated part of the singular value decomposition comes in finding these other two. Now, let's start with V transpose. Well, V is the ordered unit singular vectors of A. Now, I say ordered here because it's quite important. These singular values need to be in descending order, and the singular vectors should be in that same order. The corresponding singular vectors should be in that same order. And if they're not, this will not be this equality will no longer hold. So we just take the transpose of that, so V transpose, transpose, transpose. So these are just your singular vectors. They can be calculated because they're just the eigenvectors of A transpose A. Now what's this last one, U? Well, to find each vector in U, for instance, let's say we want to find the first vector in U. U1 equals AV1 over sigma. Now, what does that mean? Well, we know that AV equals U sigma. And we also know that because of a lot of these matrices are diagonal, if we're just looking at U1 and sigma 1, that should look more like a U there, and this is just going to be AV1. So that's how we figure that out. And the proof is much more complicated than that, but that's what we're going to stick with. So, the singular value decomposition involves calculating the singular values and arranging them in this matrix sigma appropriately, calculating the singular vectors of A from A transpose A, and then transposing them. And then with each of these singular vectors, calculating an equivalent U using this equation. And this has various applications. Now, when you come to calculating this, it's not as simple as just remembering all of this, because you have to go in and calculate all of these values. And that's why I'm not going to calculate an SVD on Microsoft Paint here with you, because that would be very messy, and you need very clear working for this because it can get quite complicated. But as long as you remember, sigma is our is a block matrix of the singular values and a zero matrix to make it the appropriate size. V transpose is the transpose of V, which is made up of the singular vectors of A. And U, for every U, if U is, U1, U2, U3, so on, U1 is A V1 over sigma 1. This has been a brief explanation of what the singular value decomposition is. I may upload an additional video, which I'll link in the description, of me calculating a singular value decomposition. It'll probably be on paper, and what that looks like. Anyway, thank you for watching.